Distribution. It's the electric utility's retail delivery system, the network that carries the nation's electrical energy to all the places where people live, work, and play. Transmission systems, which carry power cross-country, are bigger and more spectacular. But distribution is truly the bread and butter end of the business. A small but growing part of the distribution system is underground, but the overhead system still carries most of the load. Overhead line construction practices can be simple or very complex, varying considerably with individual utility standards. Affecting the exact construction materials to be used on an individual distribution pole are voltage level, number of circuits, conductor size, span length, wind and ice loadings, terrain, load locations, and population density. Even the number of pole structures is not uniform, but will normally range between 16 to 30 structures per line mile. This presentation will acquaint the relative newcomer to the electric utility industry with sub-assemblies typically found in overhead distribution lines. A vast majority of overhead distribution lines are placed atop wood poles, normally ranging from 35 feet to 55 feet in overall length. Most structures will consist of the following sub-assemblies: the conductor support and insulation system, neutral wire and grounding system, and where conductor angles or storm protection dictate, a guying system. Simplest of all is the single-phase line with conductor angles of less than 5 degrees. Normally, these single-phase lines use one pin-type insulator mounted on a steel pole-top insulator pin. The insulator pin is fastened to the pole flange side out for maximum cantilever strength. The attachment is made with machine bolts, square washers, and lock nuts. The conductor is tied to the top groove of the insulator by formed wire ties. The neutral wire is generally one conductor size smaller than the main conductor. One method of attaching the neutral wire system is a porcelain spool insulator on a single upset bolt with a square washer and lock nut on the opposite side of the pole. The neutral wire is tied to the spool with a formed wire tie. On most rural systems, a ground wire assembly is connected to the neutral wire and then stapled to the pole. At ground level, it can be connected to a driven ground rod. Or, the ground wire can be extended to the butt of the pole and connected there to a formed copper ground or ground plate. As the conductor angle becomes more pronounced on an individual structure, both the conductor support system and neutral wire system change to allow for the transverse loading. When the conductor angle is more than 5 degrees, a guy assembly is usually added, splitting the angle of the conductor legs to distribute this load equally. The guy angle should be between 45 to 60 degrees, with 60 degrees being the minimum. One method for spotting the anchor location can be accomplished by pacing away from the pole approximately 1/3 of the ground to guy attachment point, resulting in a 60-degree angle. Here is a typical single-phase structure with an angle between 5 degrees and a maximum of 30 degrees. The conductor support and insulator assembly has been doubled. 2 pin-type insulators atop 2 pole-top insulator pins mounted on opposite faces of the pole by machine bolts, lock nuts, and a pipe spacer which extends the machine bolt nut beyond the flanges of the pole-top pin. The conductor is attached to the side groove of both pin insulators with the tie over the armor rod. An additional machine bolt assembly will often be used at right angles to the bolts used to fasten the pole-top insulator pins to prevent splitting of the pole. The guy assembly consists of the appropriate type anchor and anchor rod, an anchor rod eye, bonding clamp and a formed wire grip at the ground level of the guy strand, and a guy hook, machine bolt, square washer, and lock nuts at the pole end of the guy strand. In areas where pedestrian or vehicular traffic is normal, or in cattle grazing locations, a guy marker is installed as a more visible indication of the strand. The neutral wire assembly on this slight angle structure includes an insulated clevis, spool insulator, machine bolt, square washer, and lock nut. The neutral wire is tied to the spool with formed wire ties. The ground wire assembly would also connect to the neutral wire. When the conductor angle is between 30 and 60 degrees, either porcelain or epoxylator dead-end insulators are used in a horizontal configuration. This type of structure is frequently called a running corner. In this instance, the conductor is insulated from the ground by using two 4 1/4 inch diameter porcelain dead-end insulators. A bolted angle insulator clamp is used on the hot end of the line to clamp the conductor. The insulators are fastened at the pole end with a shackle oval eye bolt, square washer, and a lock nut. Two 6-inch diameter porcelain dead-end insulators could be used in place of the two 4 1/4 inch insulators. Or a single epoxylator dead end could be used as the insulating medium. Again, a guy assembly is required, consisting of the appropriate type anchor, anchor rod, bonding clamp, and formed wire grip at the guy end, and a formed wire grip, guy hook, machine bolt, square washer, and lock nut at the pole end. A guy marker may also be required. The neutral wire assembly includes a swinging insulated clevis with a spool insulator. The neutral wire is tied to the spool with a formed wire grip. The clevis is mounted to the pole with an oval eye bolt and a lock nut. When the conductor angle ranges between 60 and 90 degrees, two assemblies of dead-end insulators are used. The conductors are dead-ended into the pole and are joined together by a jumper wire, which carries the current between the two legs of the dead end. The dead-end insulators used can be either two 4 1/4 inch diameter porcelain dead-end insulators per leg, or two 6-inch diameter porcelain dead-end insulators per leg, or one epoxylator dead-end insulator per leg. In all three cases, a dead-end insulator clamp would be used on the hot end of the insulator assembly, and the insulators fastened to the pole with oval eye bolts, square washers, and lock nuts. In high lightning areas, an additional porcelain insulator or longer length epoxylator could be used. The conductor can be dead-ended with a quadrant-style dead-end clamp or a straight-line style dead-end clamp. The connecting jumper assemblies are joined to the conductors with electrical connectors. Two different methods of guying are used on these corner dead-end structures, depending upon the mechanical loading requirements. Two separate guys, one each in direct line with the conductors. Or a single guy splitting the angle of the conductors. Each guy assembly would normally consist of the appropriate type anchor, anchor rod, bonding clamp, and formed wire grip at the guy end, and a guy hook, formed wire grip, machine bolt, washer, and lock nut at the pole end. The neutral wire is attached to the spool insulator in the swinging clevis with a formed wire grip. The clevis assembly is joined to the pole with an oval eye bolt. When a single-phase dead end is required, with no continuation of the conductors, a similar construction to the corner dead end is used, with only one string of insulators. The insulator assembly used could be either two 4 1/4 inch diameter porcelain dead ends, two 6-inch diameter porcelain dead ends, or a single epoxylator dead end. A dead end insulator clamp is used on the hot end with an oval eye bolt, washer, and lock nut used to fasten the assembly to the pole. The guy assembly, in direct line with the conductor, utilizes the same components as on the corner dead end. A neutral wire assembly is used, similar to that used on the corner dead end, including a swinging clevis and spool insulator. When moving from single-phase to multiple-phase, most commonly three-phase lines, A very similar construction is used to those which have just been reviewed. The significant difference between three-phase and single-phase is the spacing required between individual conductors. Crossarms are used to achieve horizontal spacing. Again, we will use conductor angles to differentiate the various types of structures commonly used. Three-phase lines with conductor angles from 0 to 5 degrees are normally mounted on crossarms. The center phase is supported by a pole-top pin with the same components as a straight single-phase line. The two outside phases are supported on crossarm pin assemblies, each consisting of a pin-type insulator and steel crossarm pins and formed wire ties. The wood crossarm is fastened to the pole with a machine bolt, washer, and lock nut, and with two crossarm braces and the necessary machine or carriage bolts and lag screw. A guy is normally not required for these straight-line poles. When loads exceed 2,000 pounds, such as found with larger conductors, crossarm clamp pin assemblies are used in place of the bolt-through crossarm pins to support the pin-type insulators. The neutral assembly consists of the same components as on single-phase straight lines. When the conductor angle changes from 5 to 30 degrees, most of the component quantities are doubled to support the transverse load. The center phase is supported by two pin-type insulators and pole-top pins mounted on opposite faces of the pole and is tied to the side groove of the insulators with a tie over the armor rod. Two wooden crossarms are required for the outside conductor support, utilizing pairs of insulators, crossarm pins, and conductor ties. The two crossarms are joined together and properly spaced with double arming bolts and washers. If the transverse load of the angle conductor exceeds 500 pounds per pin, the center phase is moved down to insulators mounted on the crossarms, requiring longer wood crossarms. A guy assembly similar to that used on single-phase lines is required on this angle construction. The neutral wire assembly is also the same as used on single-phase lines with the same angles. When the conductor angle is between 30 and 60 degrees, the construction changes to a running corner, with the three conductors arranged in a vertical configuration. A taller pole than that used on single-phase is required for the vertical spacing. The insulators used could be 4 1/4 inch porcelain dead ends, 6 inch porcelain dead ends, or epoxylator dead ends. Angle insulator clamps are used on the hot end of the insulators and anchor shackles, ovali bolts, washers, and lock nuts on the structure end. Normally, two sections of guy strand would be used, joined to a common anchor at the ground end. The eye on the anchor rod would be a twin-eye configuration to accommodate both strands. A swinging insulated clevis and spool insulator would support the neutral wire system. On three-phase lines with conductor angles of 60 to 90 degrees, this corner dead-end construction would normally be used. Utilizing either 6-inch porcelain dead-end insulators, 4 1/4 inch porcelain dead-end, or epoxylator dead-end insulators. In many instances, both the middle and bottom phase will include an extra oval eye bolt and eye nut to give additional climbing clearance on the pole. Two guys are normally used on each leg of the dead end and are joined to a common anchor rod eye at the ground level. And the neutral assembly is identical to that found on single-phase corner dead ends. Three-phase double dead ends can follow a multiplicity of options. A frequently used construction would be this cross-arm construction. Various sizes of dead-end insulators could be used. The center phase would be dead-ended on the pole with pole-top pin and pin-type insulator mounted to the side of the pole for supporting the jumper. Oval eye bolts and eye nuts will give additional climbing clearance. The outside phases are dead-ended into the double crossarms. Guying systems would not normally be required because of the balanced load. The neutral wires are supported by a swinging clevis on both faces of the pole. Introduction of electrical apparatus into the distribution circuits adds a number of new components into the pole's bill of material. Most frequently, the apparatus will be clustered around a pole-top transformer used to step down the voltage from the primary to secondary voltages for customer service. In the simplest transformer tap, a hotline clamp, cutout and arrestor, transformer, transformer mounting bracket, and secondary connection assembly will be utilized. The hotline clamp connects the jumper wire from the main line conductor to the transformer protective equipment. The clamp can be installed or removed with a hotline tool. A bail clamp can be used on the main line conductor with a hotline clamp connected to the bail. In this installation, any pitting or burning will occur on the bail rather than the conductor. The lower end of the jumper is attached to the cutout arrestor combination utilized to protect the distribution equipment from faults or overloads. The cutout arrestor is mounted to the face of the pole with a bracket that gives additional clearance for the cutout arrestor unit. Or, where separate cutouts or arrestors are used, a combination standoff bracket supports both units with a single bracket. An additional section of jumper wire is connected to the transformer bushing. The secondary connection is made from the secondary tap to the secondary conductors, which can be either in a straight line or dead-end configuration based on load locations. A three-phase transformer tap has most of the same components with these major changes in construction practices. The primary conductors are dead-ended on a cross-arm. The three cutout arrestors are mounted in a horizontal configuration on a cross-arm. The three transformers are mounted on the pole, in this example with a cluster mounting bracket, and are connected to the secondary conductors. The increasing use of underground distribution circuits involves the use of dip poles or riser poles as a transition point from overhead conductors to underground cable. The primary conductor support and protective equipment is similar to the single-phase transformer tap. Where the bare overhead conductor is connected to the insulated underground cable, a cable terminator is utilized. The underground cable is then protected at the ground level of the pole by a steel or plastic cable guard. A three-phase overhead to underground dip pole differs from the single-phase assembly by the introduction of a second cross-arm to support the three cutout arrestors. The three cable terminators are mounted on a common bracket. The underground cables are protected by a single riser guard. A wide variety of switching equipment is used on distribution circuits, ranging from this simple hook-stick switch on single-phase lines to the use of group-operated switches on a three-phase sectionalizing point. On this particular installation, the three primary conductors are dead-ended into the switch bases. The entire three-phase line can be switched by operating the control assembly to isolate, reroute, or pick up a section of line. This videotape has emphasized the overhead distribution portion of the power system. The structures reviewed are typical of those used by many utilities, but construction standards vary between each individual utility and location. Your chance representative can assist you in identifying these utility needs.